Okay, so we start with the last of these tests, and it's called the root test. This is used in very specific situations when the terms have exponents, and exponents obviously of k. So the root test says the following. So let summation ak be an infinite series, and this time we find this guy rho equals limit k going to infinity the kth root of ak. This is basically means you take ak and you raise it to the power 1 over k. The kth root means raising to the power 1 over k. And then you take the limit and then you find the number rho. So if rho is less than 1, the series converges. If rho is greater than 1, the series diverges. And just as before, if rho is 1, the test is inconclusive. So, before we take an example, let me remind you that a geometric series also falls under this category, geometric series. So let me sort of make up something. Suppose we are looking at 5 times half raised to the power k. So you could use the root test, but it's really not worth it because notice, although we have the exponent of k, but what is it that is raised to the power k is a constant. And when you have this base as the constant, then it's really not worthwhile to use the root test. If you do use the root test, obviously it'll give you the correct answer because the kth root of this guy is obviously going to be half, which is less than 1. But so we don't invoke the root test for geometric series. We know better results because here we can even find the sum itself as, if you remember, a over 1 minus r. So what kind of a situation do we really need the root test? So let's look at these two examples. So let's start with the first one. Now notice that it has the exponent and the base is not a constant, it's got k's in them. So it'll require a little bit of algebra. So first thing is, as usual, let's pick up our ak. ak is this complicated looking thing. Now what do? We have to find the limit k going to infinity ak raised to the power 1 over k. So again, as before, we just hold off to this for later, and let's just do ak raised to the power 1 over k. So what is that? Well, 3k over 4 minus 2k raised to the power 2k, and then raise this whole thing to the power 1 over k. We know this, that a raised to the power n and then raised to the power m is a raised to the n times m. So same idea. So I'll be left with 3k over 4 minus 2k times, I'm raised to the power 2k times 1 over k. So how convenient. It becomes 3k and then the exponent is simply 2. So now we have to find this limit. So this is an algebraic simple expression, and so now we are ready to find the limit. So as usual, I'm going to divide the numerator by k and the denominator by k. So I'm going to divide this guy by k and this guy by k. So I'll be left with 3 over 4 over k minus 2 whole thing raised to the power k. So now let's take k to infinity. So when we do that, raised to the power 2. So now as k goes to infinity, I'll be left with 3 over 0 minus 2 squared, and that will be 9 over 4. Now this is clearly greater than 1, therefore this series diverges. Now let's look at the next example. So here ak is k raised to the power 1 minus 2k over 4 raised to the power 2k. Now before we start working on this, let me give you a side result. And it says that limit k going to infinity, k raised to the power 1 over k is 1. Now how we can see this is through L'Hopital's rule. But when we did L'Hopital's rule, we didn't do many kinds of situations where L'Hopital's rule can be used. But this can be shown using L'Hopital's rule. The idea is this. So as k goes to infinity, what do we have? We have a situation where you have infinity because k is going to infinity and raised to the power 1 over k. Now as k goes to infinity, 1 over k is going to 0. So it's infinity sort of raised to the power 0. So this is not clear what it's going to be. But by using L'Hopital's rule, we can show that it actually turns out to be 1. Okay, so let's keep that in mind. Usually we need this kind of stuff in the root test. Okay, so now I need to take ak and raise it to the power 1 over k. So that means I have k raised to 1 minus 2k over 4 raised to the 2k. This whole thing is raised to the power 1 over k. So again, from your rules of exponents, you know if you have a over b raised to the power n, then a gets n and b also gets n. So that's exactly what I'm going to do here. K raised to the power 1 minus 2k, this one will have, and down below this guy gets 1 over k. Okay, so I have k raised to the power, now 1 minus 2k gets multiplied by 1 over k. So I have 1 over k minus 2 divided by, now here you have 2k multiplied by 1 over k. So that is simply 4 squared. Okay. So what is, so the numerator is k raised to the power 1 over k times k raised to the power negative 2 divided by 16. So I can rewrite it k raised to the power 1 over k. Okay, so I have k raised to the power 1 over k, and k raised to the power negative 2 means it can come down, 16 k squared, and now I'm ready to take the limit k going to infinity. So when that happens, the numerator, as we just discussed, goes to 1, and below in the denominator it goes to infinity, because 16k squared definitely goes to infinity. So you have a situation of rho being equal to 0. So this is less than 1, and therefore we have convergence. So the series converges. So we did 2 examples to show how the root test is needed when you have series of this kind. However, this is not an important test, and it has very specific use. So we don't pay too much importance to it. Okay.